Chapter 8, Lesson 3 of Advanced Algebra, and we want to look at two applications of the logarithmic functions as well as determining the inverse equation of a when we're given a logarithmic expression. Two applications that are very common are the pH or the acidity levels of liquids and the Richter scale. Now, living in California, you've probably heard the Richter scale used quite often is in the measure of an earthquake or the size of an earthquake. A 2.4 earthquake as opposed to a 5.7 earthquake. Well, what is a 2.4 and what are the 5.7? What are those numbers actually? And the 2.4 and the 5.7, when you're talking about the magnitude of an earthquake, are actually the exponents of a base 30 number. In other words, the 2.4 is the exponent of a base 30, so 30 and a 2.4 earthquake, and let's say a 5.7 would be 30 to the 5.7. So the 2.4 that they say in the news report or the 5.7, they're actually just talking about the exponent of the base 30 number. Now, this 30 to the 2.4 power is the amount of energy that's released from that earthquake, and then this would be 30 to the 5.7. So you can realize that a 5.7 is quite a bit bigger than a 2.4, even though the exponents themselves aren't too far apart, because we're actually raising a base 30, we're multiplying 30 by itself 2.4 times here as opposed to 5.7 times here, and you realize as you've done exponents before that the more times you multiply it together or multiply a number by itself, that number gets rather large rather quickly. So when we're asked to compare earthquakes then in this lesson, we're actually going to be comparing these exponents. So actually it's just going to be what's the difference between these two numbers, so you're just going to subtract them. So let's take a look at an example. You'll see what I mean. So in 1812 we have an earthquake that's a 7.9 that shook Madrid, Missouri, and we want to compare that to these other earthquakes that were in 1906 in San Francisco and in Chile in 1960. So what's the difference between a 7.9 and a 7.7? So in order to compare the amount of energy, we want to compare the exponents. So we're simply going to subtract the exponents. So this was a 7.9 minus a 7.7, so that's a difference of 0.2. Now that's a difference in exponents. What's the difference in energy? We then take this exponent and apply it to its base number, which is a 30. So we would raise 30 to the 0.2 power, and that's the difference in energy that would be released in those two earthquakes. So that would be about a 1.97 times more energy if you raise 30 to the 0.2 power. So that's a fairly simple application. To compare the earthquakes, we simply subtract the two exponents and then apply that to a base 30 number. Another common application of the logarithmic function is the pH or the acidity level of a liquid. And the concentration of hydrogen ions in a substance is what increases the acidity levels in a particular substance. And there's an equation that you'll have to remember, and that is the pH of a substance is equal to the negative log of the concentration of hydrogen ions. So we have two variables. We have the pH number that would be substituted in here, and then we have the concentration of hydrogen ions substituted in here. Now, once you substitute in a pH value, then it's simply a matter of evaluating the logarithmic expression, which we've done before. So we would substitute in the pH balance or value that's given to us. We would divide by -1 to remove the negative sign. That would move the negative sign over to the pH side, and then we're simply, as I said, solving or evaluating a logarithmic expression, which we've done previously. So let's do one example here where we have pH of soy is 4.9. So what would be the concentration of hydrogen ions? So we're simply going to take the pH of 4.9, substitute it into our expression. So the pH is equal to the negative log of the hydrogen ion concentration. So now I simply solve this equation. So I'm going to divide by -1 to remove the negative sign. So that's going to give me -4.9 is equal to the log of the hydrogen ion concentration. And as I said, now we simply have a logarithmic expression that we need to evaluate. So we take the base, so the base here is a common log, so it's 10. So 10 to the negative 4.9 power, that's the exponent, will give me this x value, or this concentration of hydrogen ions. So we would then raise 10 to the negative 4.9 power on our calculator. So if we take, let me put this down. So if we take 10 and we raise it to the negative 4.9 power and enter, that gives us 0.000013. Now you're going to have to change that to scientific notation, so we'll need to move this decimal point over 1, 2, 3, 4, 5 places so that that number is between 1 and 9. So that would be 10 to the negative 5, or 1.3 times 10 to the negative 5, which would be letter D. The last thing we'd like to look at in this lesson is how do we take an equation that has a logarithm in it and find its inverse. You remember, to find the inverse function of an equation, we make the y value an x, or the y variable an x, and we make the x variable a y, and then we solve for y. So we're going to make this y and x equals log base 4 of, and we make this a y, and now we solve this expression for y. So you remember that to solve a logarithmic equation or a logarithmic expression, we change it, we do its inverse, we change it to exponential. So we change this logarithm into its exponential form. So the base of this expression is base 4. The exponent of 4, remember, is this value that's over here. And then so 4 to this power gives me this value here. And so we have the inverse function. 4 to the x is the inverse of this expression here. This is the logarithmic form. This is the exponential form. Exponential is the inverse of logarithm. Let me do one more example where I show you something that's kind of a little trick you have to remember to do when you're dealing with some of these equations that you have to change into exponential form. In this case, we want to take this equation that has a logarithm in it and change it into its inverse, or find its inverse function. To find the inverse, we make the y an x, and then we make the x a y. So we change this out, and then we solve for y. And again, to change a logarithmic function, or to solve one, we have to change it to its exponential form. So this is base 10. So base 10, this is the exponent of 10, is equal to 10y, and I'm solving for y. So now I'm going to divide by 10. Now this is where you have to be careful. This is 10 to the x, then divided by 10. And you cannot reduce these because this is 10 to the x. So what do I do with this? Well, you remember this would be 10 to the first power. And what do we do when we have the same base? What do we do with the exponents? We subtract them. So we would make this as 10 to the x minus 1 power then. So this would be the inverse function given this logarithmic equation to begin with. Okay, so when you have the same base, you can move them to the same by applying those exponential properties that we know.